Hey Chem Kids, trying something new. I know some of you guys were absent and I've got a lot of questions about electron configuration, so I thought this might be a helpful way to get some tutoring even if you aren't able to come in for tutoring. So just first a little bit about what we're talking about. When we talk about electrons, we care about a couple things. We care about what level, we care about what level the electrons are in. We care about within that level what sublevel. And within that sublevel, for the orbital diagram, we care about what orbital. Sorry. Handwriting's a little tough. I'm writing on my iPad. So, first of all, when you look at the periodic table, in terms of levels, we've got the n levels. They're basically written here on the side of your table. So n equals 1, n equals 2, n equals 3, 4, 5, 6, and 7. Those levels carry across, so this would be the 2p, the 3p, the 4p, 5p, and 6p, just going right along with the rows. You might remember from class, and I know this is a point of confusion, that when it comes to the D block, though, which is this section right here, that the levels are shifted. So even though it's in the fourth row, this is the 3D, the 4D, the 5D, and the 6D. The F block is shifted down twice, so even though this row right here is in the sixth row, this would be the 4F, and the bottom of the table's cut off. We're not going to deal with those a whole lot. So those are the levels. Now in terms of, we got levels. In terms of sublevels, I'm going to use a highlighter here, and we're going to break the periodic table up into regions. So this region here, let me use a little better color, is 2 electrons wide. That's what we call the S sublevel. So those are the S sublevels. So that means the top row here would be the 1s, the 2s, and so on. The next most energetic level is the P sublevel, which is this section over here. You can see that there are 6 electrons across. That would make this the 2p, the 3p, the 4p, and so on. In the middle of the table, we have the D block. In the middle here, we've got the D block, which you can see is 10 electrons across. And like we said, this is an exception. So even though this top row is in the fourth row of the periodic table, this would be the 3D, the 4D, etc. And we're not going to talk about the F for now, but it's that section on the bottom of the table. So what we would need to do with this, practically speaking, on the homework and on the test, is if I asked you to write the electron configuration we'll start with something a little simple, for fluorine. So if you're going to try to write this for fluorine, we can see that fluorine, hopefully, has 9 electrons. And what we care about, again, is what level are those electrons in, and what sublevel are those electrons in. So to start with the full configuration, you read left to right just like you would at in a book or something like that. So we're going to start here, and that is the 1s. And remember, helium kind of belongs here for this. So we've got these 2 electrons, the one that hydrogen and helium would get first, and that's the 1s. So for fluorine, we'd start with 1s, and there are 2 electrons there, 1s2. A way that I've explained this before that some students have found helpful is if you think about it like, okay, fluorine's got these 9 electrons. If it only had 1, it would be like helium. If it had, hydrogen. If it had 2, it would be like helium, 3 like lithium, 4 like beryllium, boron, carbon, nitrogen, oxygen, fluorine. Those are the 9 electrons. So we're just trying to represent where those are located. So we got the 1s, 2, then you go to the next row, here's the 2, and there's 2 electrons there, 2s2, and then here we're in the 2p, but it's only these 5. You can see it doesn't have that 10th electron like neon, not unless it ionizes. So we'd have 2p6. So we'd have 1s2, 2s2, 2p6, and this would be for fluorine. As a side note, 2p5. Hopefully some of you were catching that. 2p5. If we did fluorine ion with a negative charge, which remember fluorine would gain an electron, it would be 1s2, 2s2, 2p. That would be 2p6. Okay. So let's try something a little more complicated. Again, feel free to fast forward, rewind, pause, whatever you need. I'm going to erase all of our cheat sheets here. Hopefully if you need to, you can get out your notes and look at the kind of the mini periodic table we annotated some stuff on. That'll maybe help you if you're getting stuck. So what if we tried something like, let's do arsenic. Let's do arsenic here. So I've got arsenic. Arsenic's all the way down in there with 33 electrons. So I would start here again. So I'd start hydrogen, I'd see, okay, what's this? Well, that's the first row, and I've got 2 electrons. So that'd be the 1, it's the S block, 2 electrons. Then you go to your next row. What's that? Well, that's the 2s2, and then you go all the way across. Well, what's this? This whole section is full. That's the 2p6. You go to the next row, 3s2, move all the way across. This is the 3p6. We go here, there's the 4s2. Now remember, this is an exception, so this would be the 3d10, and then there are only 3 electrons here, 31, 32, and 33. So this is we're at the 4p, but instead of 6, we would put 4p3. Okay. Now once that is written, we can also draw condensed or valence configuration. So remember, arsenic's what we're looking at. To do the condensed configuration, you find the noble gas previous. So if I look backwards, you can see I skip up to this level, I end up finding argon. Argon is the last noble gas. So I'm going to use argon for my condensed configuration. Argon is everything here. Argon is all of, oops, a little too far. Argon is all of this. Okay, and then that's where it ends. So after argon, I'm going to continue 4s2, 3d10, 4p3. Saying it's just like argon, but it's also got the 4s2 electrons, it's got a full 3d set of electrons, and it's got 3 electrons in the 4p. Okay. Now the thing I had the most questions about was valence. So just thinking about valence. Valence is the outermost level. If you look at either of these configurations, you see that the outermost level is 4. So the valence configuration would simply be 4s2, 4p3. So arsenic here would have 7 valence electrons total. So with this, we could say there's 7 valence electrons. And I can't do math. Hopefully you caught me on that. That would be 5 valence electrons. So if I asked you to draw the Lewis dot structure, which we learned on Monday, you'd say arsenic, pen isn't working, 1, 2, 3, 4, and then you'd pair up the last one to represent 5 valence electrons. If arsenic ionized, you can see that arsenic would gain 3 electrons to be like krypton, so we'd put in the 1, 2, 3, giving a charge of -3. Just to talk just briefly more about valence electrons. I'm not going to try to do orbital diagrams on this because I think I would run out of space. But just talking about valence electrons. Everything in this column here, these are all going to have 1 valence electron. Everything here, they're going to have 2 valence electrons. Reason being, everything in this first column is going to be something S1, if you ask the valence configuration. Everything in the second column is going to be something S2. Here we've got 3 valence electrons, then 4, 5, 6, 7, 8. That's a pattern that you can use instead of having to figure out every time. For example, something here like sulfur. Sulfur has these electrons in its outer shell. That would be the 3s2 and the 3p, what's that, 4. And that makes 6 valence electrons. So anyways, hopefully this is a little helpful. Feel free to email me if you have questions. It's everything we went over in class, but I know some of you guys were absent and it's hard to catch up on this stuff. So let me know what you think. Maybe we'll do this more in the future if it's something that you guys are finding useful. Good luck.